So we're going to talk about balanced and unbalanced forces and how to start drawing free body diagrams, or sometimes they're also called force diagrams. So let's just review Newton's laws before we get too in deep here with balanced and unbalanced forces. So the first law says that an object at rest will stay at rest. An object in motion will stay in motion unless acted on by an unbalanced force. This is the law of inertia. And if it's in motion, it'll stay in motion at a constant velocity, a constant speed. It will not increase or decrease speed. In order to cause acceleration, you have to apply a force. And that leads us into the second law, which is the equation force equals mass times acceleration. So F equals ma. And then also when we're talking about gravity, we can plug in, instead of A, we would plug in the little g, which is 9.8 meters per second squared. But you only use that number when we're talking about gravity. And the third law, for every action, there is an equal but opposite reaction. And those are action-reaction forces. Those are not the same thing as what we're about to start talking about for the unbalanced forces. For the action and reaction forces, you're talking about two objects interacting and how they interact. One object pushes and the other object pushes back with the same force. For balanced and unbalanced forces, we're only talking about one object and all of the forces acting on that one object. Okay. We haven't done the gizmo yet, but we have talked about when you increase the force, it increases the acceleration. And then if you increase the mass, that decreases the acceleration. So we will be doing the gizmo. You'll be doing the gizmo on those e-learning days. But those are some big ideas that we've already talked about, and you'll just be exploring that in the gizmo. So force and acceleration have a direct relationship. If you increase the force, you increase the acceleration. Mass and acceleration have an opposite or an inverse relationship. If one goes up, the other goes down. We saw that with the spaceship, or the International Space Station video. The chapstick was really, really small, and it went really fast. That larger object that he applied the force to did not move very fast. It moved really slow. So if you increase the mass, you decrease the acceleration. So forces. A force is a push or a pull. It's that simple. A push or a pull is a force. All forces must involve two objects. One object that creates the force, and one object that reacts to the force. So those are your action and reaction forces. That's the third law. Balanced forces. But like I said, balanced forces are when all the forces cancel each other out. The result is that since all the forces cancel, there's no net force being applied to the object. So if the object is at rest, it will remain at rest. If it's already in motion, it will remain in motion at a constant speed, no acceleration. So balanced forces are acting on one single object. That's not the same as the action and reaction forces. Okay, so acting on a single object, if they're balanced, all the forces cancel out. You probably have a force acting upwards and downwards on the object. Those would cancel. And you may or may not have forces acting to the right and to the left of the object. But for them to be balanced, everything has to cancel out. So looking at this tug of war, we see that these three on the left are pulling with 300 newtons this way, and these three on the right are pulling with 300 newtons this way. And so 300 and 300, those would cancel because they're pointing in opposite directions. They're pointing in opposite directions. Okay. Unbalanced forces. So when you have an unbalanced force, there's at least one force that is not going to be canceled out. Okay. So not all of the forces will cancel. So the result is that whichever way was not canceled, that's the net force. The net force is going to be pointing in a direction, and you're going to subtract all the other forces from it. Whatever's left over is your net force. And your object will accelerate in the direction of the net force. So unbalanced forces do not cause motion. Motion can be maintained without forces. Unbalanced forces cause a change in the motion of the object. So they cause a change in the motion. So they cause it to accelerate or to have a negative acceleration, to slow down. So they're causing a change in the motion. So looking at this tug of war, to the left, these guys are pulling with 400 newtons, and to the right, these guys are pulling with 300 newtons. So you can see if we subtract these two because they're pointing in opposite directions, we still have 100 newtons in this direction. So these guys would win, and they would pull them with 100 newtons to the left, because 300 newtons is canceling from here. So 400 minus 300 is 100. So our net force is pointing to the left with 100 newtons. Okay. So we know that the net force is mass times acceleration. When the forces are balanced, the acceleration is equal to 0. If it's at rest, it stays at rest. If it's in motion, it will continue to move at a constant speed. When you have unbalanced forces, then you have acceleration. If your acceleration is positive, your speed will increase. You're going to go faster. If your acceleration is negative, then you will be slowing down. Your speed will decrease. So those are things that we know from our last unit, but we're going to continue to use them when we're talking about forces and how forces can cause your object to slow down and how forces can cause your object to speed up. So when you're playing with the gizmo over the next couple of days, take note. This is going to be important. So balanced forces, there's no acceleration. Unbalanced forces, there is acceleration, and that will go in the direction of the net force. So free body diagrams, those are also sometimes called force diagrams. Those are diagrams that use vectors, or remember, those are just arrows to show the strength, the magnitude, and direction of all the forces. So the bigger the arrow, the bigger the force. So you want to try to draw arrows that are related to the size of the force. So if you have a really small force, you would draw a really small arrow. If you have a really large force, you would draw a large arrow. So vectors show both magnitude and the amount of force and direction. Okay, so magnitude is how big the force is, and the direction. So you're pointing the arrow in the direction of the force. So the longer the vector, the longer the arrow, the bigger the force, the greater the magnitude. And we want to make sure that we put little arrowheads on the end of our forces, our vectors, to show the direction. There are different types of forces. So we've talked about some forces. We've talked about gravitational force, for example. But you can apply a force, and so we would just call that applied force. That's the force that you apply to an object to get it to move. So, for example, you can push against a desk to get it to move. You would be applying a force. That's an applied force. Gravitational force is the force of gravity from Earth pulling the object down. That is known as weight. We've talked about how mass and weight are not the same. Weight is the force of gravity. And you can calculate that by doing the force of gravity, so Fg equals mass times g. And remember that g is the acceleration due to gravity, which is 9.8 meters per second squared. That's on Earth. So the force of gravity is equal to the mass times 9.8. There's the normal force. So this is the force applied to an object when it is sitting on a surface or on the ground. So even though it's sitting on a surface, gravity is still pulling down on it. But the surface is pushing back up on the object, causing the object to not move because the forces are balanced. So you have gravity pulling down on the object, and then the object, whatever it is sitting on, is pushing back up on the object. So that's the normal force, is the surface pushing back up on the object. So gravity pulls it down, the normal force pushes it up, and when those are balanced, the object is not moving. So we'll talk more about this in class. Okay. There are frictional forces. So the frictional forces work against motion, and they cause moving objects to slow down and eventually stop. So this is really important. Friction always goes against motion. So if you're moving to the right, then friction would go to the left. It always goes in the opposite direction of the motion. So this is a tricky one that we'll kind of talk about here on the next slide, I think. But if the net force is in the direction of the frictional force, the object is going in the opposite direction, but it is slowing down. So if the frictional force is winning, if the frictional force is the net force, then that means the object is slowing down, but it's going in the opposite direction. The acceleration is in the direction of the net force, but the object is moving the other way. So we'll talk about that on the next slide. Air resistance we've talked about in class. This works like friction, but it's when the object is moving through the air. It's colliding with the air molecules, and that causes it to slow down as well. Tension. Tension is force transmitted through a stretched rope or a cable or a wire. If something is hanging by a string, you're going to have a tension force, and that will work opposite of gravity. So gravity will pull the object down, and the tension force will pull the object in the direction of the cable. So usually up. Okay. Oh, so here's an example of a free body diagram. You want to draw a square to represent your object. So this is your object. We just tend to always draw a box or a square. If this object is sitting on a surface, you would have the force of gravity pulling down. And then because it's on a surface, you would have the normal force pushing up on the object. So here we're applying a force to the right. So the applied force is moving to the right. So F applied. And that means if it's on a surface, you're going to have friction going the opposite direction. So friction would go to the left. So this is just an example of a free body or a force diagram, what one would look like. And it looks like on this one, these arrows are all about the same size. So these forces would be balanced. And so this object can be doing two things. If all the forces are balanced, it could be at rest. It could be at rest, but it could also be in motion with a constant velocity. So if the forces are balanced, that just means that there's no acceleration. So it could still be moving without acceleration. It could be going at constant speed. So it could be one of those two things. Okay, so let's look at these diagrams real quick and see which direction the object is accelerating. So in our first one, we have the force of gravity pulling down, and we have tension, force of tension pulling up. So this object must be attached to some kind of rope or cable. For example, could be an elevator. Okay, and so which force is bigger? Which force is bigger? So the upward force is bigger. So that means the object will be accelerating upwards. So, and it will have a net force of about 400 newtons upwards. So the acceleration will be upwards. Okay. This one here. So we have gravity pulling down and air resistance pulling up. So this object is in free fall. This is a falling object because you only have gravity and air resistance. And so which force is bigger? So that would be gravity is 800 and air resistance is only 600. So the net force would be, when you subtract them, you get 200 newtons in the direction of the bigger force. So 200 newtons down. So it will accelerate downwards. And you can see that this arrow is bigger than this arrow. So this is the larger force. This is 800. This one's only 600. So it will accelerate downwards. Okay. And over here, this object has a normal force. So it's sitting on a surface, and it has the force of gravity. Those are both 50, so those cancel. So we won't focus on those forces because they're balanced. And then we would look at the other forces, the horizontal forces on the object. So the only force that we have that's horizontal is the frictional force. So it's 20 newtons. So the object is accelerating to the left, but because this is friction, it's going to be a negative acceleration, which means the object is really moving to the right, but it's slowing down. So it would have an acceleration of negative 20, or it has a net force of negative 20, and so your acceleration would be negative. It would be a negative acceleration. And so that means you're really moving to the right, but you're slowing down. So do be careful, because friction means that the object's going in the other direction. Okay. The acceleration is to the left, but because the object is moving to the right, that means it is slowing down. Okay. So when you're drawing free body diagrams, make sure that you consider all the forces acting on an object and only ignore forces when you're told to ignore them. So a lot of times it'll say ignore air resistance or ignore friction. When you're on a surface, remember to include normal force. When an object is falling, remember to include air resistance. When it's on a surface, remember to include friction. So those are some important things. When it's hanging from a string, make sure you include tension. So we'll do lots of practice with these in class. So now go back to the assignment on Canvas. There is a YouTube video on free body diagrams that I want you to watch. They will diagram out 5 free body diagrams, and I want you to draw them as you watch the video. They draw them too, so just copy it from the video.